Tony,
Yes, sir.
did you notice at Snug and at Cadence Live, they were doing digital twin all over the place? Digital twin this, digital twin that. Do you know anything about digital twin?
A little. I guess that's why I'm up here. I'm surrounded by all these EDA guys, and I'm here to talk about digital twin. So I did read it, and I think there's some misconceptions about what it is. I saw your blog about how big the market was.
Yeah, well, it's supposed to, Anirudh says it's huge. It's like,
But there's different levels of digital twin, meaning the digital twin of the integrated circuit and the package is important. It's necessary, but not sufficient. And what do I mean by that? First of all, digital twin is not a new concept. It's been around for a long, long time. In the space that I grew up in and did all the work I did was a simple example where digital twin started was building an automobile. Are all the parts going to go together when you stick it together?
right, but that's airflow stuff.
No, not. So is it going to go together? It used to be when you put a vehicle together, the first time you did the first build, you have a book this thick of all the problems. Interference problems, things like this, parts not fitting together.
Right.
We're way past that now. That thing's going to go together. Every nut, bolt, screw of that thing has been tested, simulated. We can put it, it's not the problem. What's happening now is, I want to know the functional characteristics of what's happening. Is that vehicle going to go as fast as I want it to go? Are the braking systems going to work like I want? Is the noise, vibration, and handling going to be where I want?
But why does an IC guy even care about any of that?
Thank you, and I'm coming to that, my friend. He's so impatient with me all the time, and then he tells me to explain stuff.
This is, it's called specifications. You make the circuit to run so fast with so much area, and I'm done. I don't need a fancy digital twin thing going on.
Right, so I'll give you a real live example of what we're going through right now with one of our customers, Sony. So Sony, the consumer products company, they're building an AR/VR headset for us today. And we're using it for 3D design. So what we talk about is NX, which is our 3D modeling system to design things in 3D space.
Okay.
They use our product to design all of their products. Right?
But that's your Siemens NX thing. That's not,
Yeah,
again,
that's 3D
I'm a
design.
chip guy.
Oh, man.
Okay.
Gosh, give me some money. This is what happened 6 years ago when I tried to tell you, and you said, I don't know what you're talking about, digital twin.
Still didn't get through.
And it's funny, he calls me up and he says, hey, Tony, they're talking about digital twin. Maybe I should listen to you this time. So I'm trying. I'm going to help you.
All right.
So,
Siemens, where are we? Siemens NX.
so you're designing this thing.
Okay.
And I just met with them a few weeks ago. And they said, Tony, I want to talk about how we take that headset into the factory. And I said, why? I said, I've got a million use cases already for 3D engineering. And I was like, why? He said, because when I get into the factory, there's a new level of noise issues I have to deal with in the factory. You think about how loud it is in the factory, and he says, my headset, I've got to know now. I've got to know the requirements that would go into that for that headset, right? Because they hired Qualcomm to build a chip. And he says, we've got requirements going to them. Now, you say, well, I can manage requirements at the chip level.
Yeah, noise cancellation circuit.
Yeah.
Okay.
But how's it going to interact with the rest of the product? All right. In other words, I've got requirements that come in at the chip level, and I can manage that in a model-based systems engineering. Do you know what that is?
Right.
So I'm tracking a V of systems engineering. How do I track back to make sure I'm doing the things I said I would do? If you're doing it at the chip level and you don't understand how it interacts with the rest of the product, you start having issues. And so my customers come to me, for example, in their case, he's saying, look, I need to know, if I want to put noise cancellation in, I might have different power consumption requirements now because I'm doing in the factory. It might change the chip design, and I have to know that at the time I design the product. I've got customers in aerospace and defense. They're designing radar systems.
Okay, wait a minute. I'm sitting there running Virtuoso, designing my analog circuit. Why do I care about what you just did?
You don't care about power and footprint?
No, it's just a spec. Okay, use less power.
I know, but your spec is being driven by the product. It's not a spec that's independent, and that product is evolving as they define it for their customer use cases. And so what I hear from our customers over and over again, you know what, this idea of building the chip and then figuring out the product, no. They're designing it simultaneously. The reason your conference is called the Systems Conference is exactly that. How do you bring those worlds together? And so we see this over and over again with our customers, saying, look, I've got to be able to know this. I've got to be able to simulate this up front. I've got to know if I've got thermal issues up front. What am I going to do? And those thermal issues are dependent on the packet, the design that I'm working with as well. So earlier in the conference with Jay, I mentioned one of our customers, one of the largest consumer packaged goods, our products companies in the world, designing those earbuds
Apple
that go
or
in your
Samsung.
ear. I'm not going to say who. That earbud that goes in your ear.
Right.
The printed circuit board that goes in that earboard has 43 bends. 43 bends. And then you got to pop a circuit on top of it somewhere that's not sitting on the bend. And then you got to put the design around it, the 3D model to design it. And then you got to figure out, do you have heat issues, build-up issues in this? That's why they come to us. And that's what we mean by a digital twin. So when we talk about the digital twin, it's not just the integrated circuit in the package, it's the product. But then I take it further. The digital twin is also the factory where it's going to be produced. So for example, when we think about what we do at digital twin in this space, the wafer bending process. You're going through that wafer bending process, you've got to categorize these dies coming out.
Right.
Some of our customers have 10,000 rules for the bending of those dies. 10,000 rules that you've got to bend. Then,
so that means everything goes in the reject bin. That's pretty easy.
No.
Okay.
But then you want to tie that. You want to tie that back to the bill of the MBOM, the bill of manufacture that I have to build.
Okay. Bill of materials. Yeah. Okay.
But there's also a manufacturing BOM that goes through this, right? So we have an MES system, manufacturing execution system, that goes on the floor, the factory floor. It tracks all kinds of things, your quality, your workloads, everything you're doing, running that foundry, right? From that bending process, I take those 10,000 variants that I have to be able to calculate, automatically map that to a bill of material, which maps to the product that it has to go to. Because some of those products are able to use the chip that maybe have lesser performance.
But this is still, I don't get as a chip guy. All right, Shankar, are you developing binning software?
I hope not, because we're selling a lot of it right now.
Okay,
so.
These are tangents that a chip guy is not going to be thinking about that. The closest we get is 3D IC.
The first digital twin, if you want to be a little humorous, was the SPICE model. Because think about it. It is basically a digital computer simulatable representation of a transistor. So if you want to really, really go way back, you can call a SPICE model a digital twin. You can call a gate a digital twin of the circuit that it represents, and you can just work your way up. So you can make this as big as you want to be. But I think the reason it is relevant today, and I agree with Tony, is that as you look at building intelligent systems that have a chip or multiple chips, they sit on a PCB, they're interacting with mechanical components, there's a big software component, and there's an AI component. How do you build this virtual product on a computer that you can simulate, that you can test, where you don't have to actually build a physical thing? For example, if you want to crash a car 100 times to know whether or not you got it right,
so instead you crash it in Synopsys software?
Crash it 10 times, right? So that's really why digital twins are important.
Well, and they're about to spend $34 billion to do exactly that, so I think somebody does care about that.
Well, how does that... Okay, with $34 billion. You really are wagering $34 billion that it's digital twin and it's not CFD?
No, it's way more than that, right?
Okay.
So basically what we are seeing is that silicon companies like NVIDIA are becoming systems companies because they're essentially selling an entire cluster with software running on it, and they have to optimize that whole entity from a vertical integration perspective. So how do you do that, right? You've got to be able to build that big 100+ billion system on an advanced package. So there you have to deal with stress issues and thermal issues and all kinds of other issues to build that. Then that has to interact with the board that it sits on, that has to interact with the chassis that it's placed in, that has to interact with the pod or the cluster that is created around it. So how do you optimize this holistically, right? You need multi-physics analysis to be able to do that. You obviously need electronic design tools to be able to do that. And so that's why this thing is so relevant, is essentially being able to look at things.
Seems like we've been doing this for the last 40, 50, 60 years.
Yeah.
I don't see what's different.
To limit,
maybe we got some better tools.
I think that,
but we've been optimizing systems back in the 80s, back in the 70s, okay? Yeah, the tools are now a little better, but I don't see anything fundamentally different.
No, but what's different is basically that the entire product development process is getting digitized, where you basically do it in a virtual environment. I mean, I just saw this.
But isn't it just a glorified management tool? So the guys upstairs can look at an entire flow and go, oh, looky, it flows like this.
I know, I think, John, there is, Shankar, that there's more of a kind of overlap as you move from the chip to the package to the board to these end systems talking about. And so we're now looking increasingly at how do we optimize across that overlap? How do we do co-optimization between the different levels of abstraction in the stack? And that you could argue maybe we've been designing systems for a long time, but we're now at a point where we want to push that envelope yet further, or we're at a point where the complexity of the physics, the scaling, the sheer size and the dimensions are such that we need to look at these overlaps. So they're coming into the foreground more. So I think there's a real pull from our customers.
Like I'll give you a simple example, right? If you did things the old way, you would first spend 2 years to build a chip, then you will start writing software for that chip and take 3 years to build the software. The new way is you start writing software pretty much the moment your architecture is locked down. You have a digital twin of the chip, essentially moving up to the software teams through a virtualized model. And then basically as the chip gets developed, the software gets developed, and the day it comes back from the fab, your software stack is working. That's digital twin in action.
And the product has to know how the software is going to work in the product. So that's the whole point. It's not just there. It's all the way to the product.
So I think there was one, certainly on the Cadence side, we called out one other point about this.
Right.
This twinning is more these analogies between these different types of twin, like as Shankar said, right there down from a model of the transistor. You've also got, to what extent can we actually leverage the same expertise, the same algorithms, the same source code, the same techniques,
right,
and bring that knowledge from one dimension to another dimension. And I think there's a lot of opportunity there. And one of the things we pointed out, like if you think of that chip digital twin, we're pretty good. So we can get the chips right first time. I mean, there's so many companies out there getting first time production ramp silicon.
So what I'm hearing here is digital twin is the hot new buzzword, and oh, by the way, we're all compliant to it.
I would say different. I would say
we're good to go along with it.
All right,
we're good to go along with it.
How am I wrong on that? Tony, how am I wrong on that?
Because it depends what you mean by digital twin.
Well, that's the thing. Each one of these people are
Right.
twisting digital twin to their own purposes.
Exactly.
Dean said, well, hell, we've been doing this for 30 years.
Sounds like simulation is digital twin.
Yeah.
Okay, I mean, we've been writing code for chips, okay, before the chips are made for 30 years, okay?
Right.
We run them on emulators, we run them write code on simulators, we've been doing that, okay? It's just, we're getting better at it. We get better at it every year, right?
And you did see some pretty big TAM numbers, and I think that was partially around this point that if we could take real mechanical systems out there, we could take whole airplanes and we could simulate the same percentage of the flight envelope that we could of a chip. I mean, there's huge upside, right?
Yeah, half a trillion a year is like incredible.
And I think that's an inspiring call to action to say, actually, what we've got in our industry, we can go there, right? Yeah. We can actually deliver that.
But I mean, all the stuff that I think is new and interesting in this zone that you guys are talking about is all mechanical, not inside the chip. Okay. Simulating a plane, simulating a car crash. Those are kind of new things.
We've got some more, but things like stack die,
simulating a car
warpage,
crash
stress.
is not
I
a
mean,
new
there's
thing.
some things at the
Yeah, I
chip
know,
level.
but I mean, like,
No, it's not.
I have to argue for Tony's behalf because they just came out with 3D IC Innovator, and
the 3D IC stuff, sure.
I mean, but that's for us. That's digital twin right now. That is stacking stuff there.
Yeah. And it's a similar
Shankar,
problem.
how can you do 3D IC without a PCB tool?
Because PCB tools are old and 30 years old, long in the tooth. They don't have the capacity to handle modern 3D IC designs, which have tens of millions of connections, several million bumps. We believe the advanced packaging design community has not been well served because they are looking for an integrated environment where you can design, explore, sign off everything in the same integrated cockpit like we did for 2D. And that doesn't exist for 3D. And so that's why we had a huge opportunity here to extend our Fusion platform, which is really the best 2D platform in the industry today, to extend it to 3D so it brings the capacity, it brings the automation, it brings the deep integration of all our electrical analysis, And now with the partnership with ANSYS brings the best-in-breed multi-physics analysis in the same cockpit. So essentially, this is the modern way of doing 3D IC designs, and the previous generation of flows and tools essentially will choke in terms of capacity because they're not built to deal with millions and millions of connections.
So it is the best digital twin.
All right. I heard ANSYS being mentioned here. Paul, is Cadence in trouble that now that Synopsys is acquiring ANSYS? I mean,
we were competing
like...
with ANSYS already, and I think we feel pretty good. I don't think we see a big change after merging with Synopsys. I think per this point, right, we called out, look, the core competencies that we have in some of our core electrical side, right, we can scale out into this multi-physics space, right? So we took the solvers in Sigrity and
some really sweet multi-physics stuff. I mean,
I agree. I think
he's dropping $31
but
billion on nothing. No, I don't think so. I think he's buying really good tools.
But you look at the build out where we've got to now, the growth that we've seen so far. I think Clarity is really differentiating in terms of scalability and accuracy versus HFSS.
Okay.
Celsius against IcePack, and now as we move, with Fidelity CFD in the kind of mechanical CFD space, we've got some nice acquisitions in there too. I mean, Cascade is some really smart people out of Stanford. We've got NUMECA, we've got Pointwise. So I think we've combined together, meshing with this evolution of the solvers and really pushing, like I think what Anirudh's done right at the beginning. If you want to do a very large, scalable, massively parallel numerical solver, we know how to do that. We believe we're the best at doing that in Cadence. So we're just kind of moving in that direction. I think now with Beta CAE, we've really put that pre and post processing. So I think we feel very, very, very confident. But we welcome the competition, right? And absolutely no question. I mean, ANSYS have a significant position, and so we're looking forward to continuing competition as we already have.
Shankar, did you buy old software that's out of date?
No, there's a really good reason why ANSYS is the gold standard in multi-physics for structures, fluids, electronics, and also semiconductor in terms of power integrity, right? And to be the gold standard, it's not like you're a gold standard 10 years ago or 5 years ago. You have to be a gold standard every day. And that's why ANSYS has the market position it has. And
well, I looked at HFSS, and the algorithms they had were kind of old and creaking. When I compared it to, when I looked at Clarity when it came out, and I did a deep analysis of it, I was like, oh my God, Anirudh's people are bringing in modern algorithms, and it seemed like ANSYS still had old stuff. And they had a customer base that was very happy with the old stuff, but it was a limited performance thing. So aren't you buying?
I mean, there's what you write in Deep Chip, John, and then there's what's reality. And so, I mean, in the end, what matters is what the leading edge customers are using. And we've done our research.
That was mean. I like that.
We've done our research, and we know that all the people who are doing complex designs are essentially using the ANSYS technology.
But that's at the HSS level.
Look, I mean, every product goes through its evolutions, and I'm a huge believer in competition, and competition makes us work 10 times harder, and any great engineering team knows how to respond to a challenge and come back doubly stronger, and that's what the HFSS team has done.
I think you'll see, and there is alignment. We feel there is a coupling between this multi-physics and the core silicon design world, so we're aligned on that point. Sometimes John writes the truth, though, Shankar.
I like you. That's good. I like that. Yay!
Shut up.
John, if I could make one comment about this, because you said something which is somewhat accurate. Humans and even engineers sometimes they fall victim to the hype cycle, and there's a big hype cycle around digital twin and AI and all this crap. Right? That is,
right.
I mean, people, it's not crap. There's great stuff underneath, but the hype cycle makes it all seem the same and crap. Let's be very clear in this marketplace about digital twin and CAE, right? Cadence isn't going to go out of business because of ANSYS and vice versa. CAE has a place there's an intersection between IC design and CAE stuff, but it's pretty narrow. It's very small if you look at the intersection in those places. And back on the digital twin, look, every good engineer on the planet simplifies their model to ignore as much shit as they can. That's the whole idea, is ignore as much shit as you can because the world's too complex, and get it so you can model and do it right. And then the world gets more complicated, and I have to creep a little bit more in. That's what's happening. That's why these, quote, digital twins, it's only at the fringes where you need the, quote, digital twin. In IC, the 3D IC packaging, for sure. If you do high performance memory stuff, for God's sake, sure you have to do something more than you had to do 2 years ago. Not because we like to do it, because you have to if you want to solve the problem as an engineer.
Because the physics comes in and starts ruining your life.
And look at the intersection. Forget the hype. Look at the intersection where the business is moving out, and you actually need to solve another problem. Don't solve problems you don't need to solve. Some of them are bullshit. And that's what the hype is about. Some actually need to be solved, or we're not going to get the next generation of product out.
Yeah, I like
Here, here.
Yeah. Speaking of hype cycles, Joe Costello.
Yes.
You're selling, well, correction.
T-shirts.
Well, you're throwing T-shirts, but I'm saying selling in a collective phrase. You're basically giving away free DSIM Verilog simulators. I don't see where is the upside for you? How do you make money? Is this just a Joe Costello stunt?
This makes Joe Costello sense. It makes industry sense. You know, sometimes it makes sense to me before the rest of the world, but it's happening. So this is the most important thing happening from my point of view. And thank you for making us number one. We appreciate that. I think it's fundamental.
Well, it caught my eye. It was really because I went through it, I did the analysis, and it was like, oh, you did the benchmark. I talked to users, I was like, okay, this is comparable to the big threes, Verilog simulators. It's working, getting numbers in the neighborhood, it works. Why the hell you're giving it away for free doesn't make sense.
But why do you give it away for free? The model in this business has to change fundamentally. And there's way more than giving it away for free. We are giving it away for free. We have a free ASIC level system Verilog VHDL simulator. You can go now, download it. That's why I'm throwing out the T-shirts. That's on the back of my T-shirt. You can QR code me if you want. Right, so, or if you,
Welcome to the hype cycle.
Memory, then there's a T-shirt for you. So, however you like to do it. But the idea is really simple. Everybody on the planet Earth, every designer on the planet Earth ought to have a system Verilog VHDL simulator at their hands, right at their fingertips. No cost, no money, no nothing. And they can use it for coding, for debugging, for doing small design work. And we don't make any money on that. You shouldn't. It's a gosh darn IDE. It's for software development. HDL is software development, for God's sake. You pay for your software development environment. Most people don't anymore. You shouldn't for HDL. Does it develop it, debug it, do your designs, small designs, it's fine. Now, 99.99% of all simulation cycles happen in some form of data center when you're doing regressions. Not for the individual engineer doing their actual creative work. That's not where the cycles go. They go at the back end on regression. So when the engineer wants to do the creative work, free them up. Let every engineer on the planet Earth, every single one, have a great system Verilog VHDL simulator to actually do their work and create. If you're in a big company and the assholes won't let you use it at work, get it at home and play with it at home, right? You can do it anywhere you want. That's the deal, right? Anybody on the planet Earth can have one. That's how it operates, right? Now, if you need more power than a single machine, go to the cloud. That's the other message here. You shouldn't be using some half-assed data center with limited access. You should be going to the cloud where there's almost infinite compute capacity, and it should be cheap. So you couple a free simulator on your desktop for all your coding and debug work with a very inexpensive cloud when you've got to go and do massive things. Bingo, the world changed. And the whole idea behind this is really fundamental. When I got involved with electronic design automation at the beginning, it was fucking exciting for engineers. It was the coolest thing that happened. You had tools on your desktop you could play with. Engineers loved it. They were free for the first time. And that has gone away. This is the whole idea of setting people free. You've got a tool, you can do it. You can be an engineer all by yourself, and you'll have more compute power at your fingertips going to the cloud than engineers sitting at NVIDIA and Intel today. No joke. So that's the idea. Have a free tool, do your design. If you need to do something big, boom, to the cloud. You have almost infinite resources, and it's friggin' cheap.
So I'm free at 1.5 cents a minute. Which is actually not that bad.
Or cheaper.
Right.
Or cheaper.
Right.
By the way, they wouldn't let me have my t-shirt gun. It was against the DAC rules, so I can't get all these.
Shankar, are you in trouble? The same thing. Paul, are you in trouble? He's going to sabotage your whole Verilog simulation market. Should you just shut down this? Just give it all to?
They're not in trouble. They have their country clubs.
Get a T-shirt.
Right? They're not in trouble.
So
It's cool. They're all good.
I do want to use the opportunity to correct something that you wrote, John, which is not true, which is
Again?
in the spirit of open discussion, right? So you claimed that none of the EDA vendors offer a pay-per-use model for on the cloud for simulation, and that is not true.
You guys have cloud. I know, but
from 2022 we have offered simulation pay per minute on the cloud. So that model is already available and is available to customers that want to have access to it. Since
So
2022.
did Shankar just undo
Both
your?
of us, we do that, yeah.
All right. So Paul says Cadence has that. Shankar has Synopsys has that.
And so
Costello
what's the
says-
price, guys? What's the price per minute?
I'm happy to compete every day with their version of the cloud model. Ours is,
So-
we give you all the
Yeah,
tools
I
to-
don't know about Shankar's thing, but I mean, our experience with that, because I think that going to a SaaS-based model has a lot. I loved actually your very simple way to explain cloud magic math.
Right.
That you can move it elastically. You can run a lot more licenses in
Yeah, it
parallel.
was like
less, and
cheap
it's
as
the same
hell.
cost.
I was like, great.
You know, that has a lot of powerful value in verification,
Right.
especially. But it is really hard to, at the end of the day, our users, they'll just decouple. They'll say, okay, well, how much compute was run? What would it have cost if I rented that compute myself directly outside of Cadence, or if I bought the data in my own data center? So they kind of break it all down and then look at basically this is the license cost, this is the hardware cost.
one of
and
the
so on.
nice
So
things.
that's what we find happens all the time. I don't know what Shankar finds.
One of the nice things DSIM does, what Metrics does, is they just take care of the cloud stuff. It's automatic. I can just
So
upload
we
it.
have all that, but it doesn't mean
I
when
have
you
to do
negotiate-
negotiations with you and get a license for tokens and blah, blah, blah.
Lots of asterisks. Go for the asterisks or go my way.
So I do actually like, I think and I actually applaud what Joe is doing, and if I was running Metrics, I'd have exactly the same strategy. I think it's trying to drive more of a SaaS-based, consumption-based use, particularly for peak. It's a really interesting thing, and it could be very valuable for the market. And I think if you can accelerate that, Joe, that's good for all of us.
Good. And everybody, try it. It's no joke. Part of the problem is people don't quite get it yet. This is not a joke. It's not a gimmick. We're not doing it as a one-time come on, and you're going to pay later. None of that. It's for real. Anybody can go download a free, full-on Verilog, System Verilog VHDL simulator, use it as long as you want, upgrade it as many times as you want, and then we give you free minutes to go play in the cloud, get a feel for that, and it is push button. It is push button. That's really important, to make it push button. We worked really hard for years to make it push button up to the cloud, and it's cheap in the cloud. We are announcing here, we actually are doing a partnership with Altair here. We're doing a partnership, we can also do it in your own data center. If you want to run at your data center, you insist on not going to the cloud and run your own data center. God forbid, people used to think real men had fabs. Real men shouldn't have their own data centers for sure, right? It turned out they shouldn't have fabs either, right? But so you can go use the cloud whenever you want.
Dean,
Yes, John.
all these guys, Cadence, Synopsys, even Siemens, they have some form of IP management, and Keysight's even doing one. They do data management. Is your product dead?
Not last time I checked.
All right.
No,
seriously,
So we
I
have,
mean, IC Manage is-
IC Manage has multiple products. We have a design management product, we have an IP management product, and we have a holodeck product for bursting into the cloud. So which product are you talking about, John?
Costello will burst you into the cloud in any which way you want. And apparently,
Yeah,
so will
if your
Cunningham
design is like
and-
10 or 20 files,
All right.
okay, but my design's a terabyte. How do you get that into the cloud? Okay.
Joe?
One of our customers was doing x86 designs, and they moved to 6,000 servers in the cloud, and it wasn't a problem.
Yeah, how long did it take for the data upload, right? How long does it take to transfer a terabyte from your home server okay, and massive libraries to
saying
cloud. It's a big issue. All right?
I'm not saying there's not ways to do it better, but
Yeah.
Well, that's one of the things that Dean's company does is he says he can upload much faster because it's a lot of duplication is gone.
Right. Yeah.
And
So we run. We have a product at Holodeck that complements the EDA vendors' cloud bursting solutions. These cloud bursting solutions are all really awesome. Okay, and changing us to a SaaS model, I think, is going to be a great thing. But there's a big issue with moving the data. Right? The designs are big. It's unclear which data is needed to run which simulation. Okay? And so most of the EDA vendors kind of outsource this problem to NetApp, Pure Storage, Azure HPC, Amazon FSx, and it's not particularly good. And Holodeck solves those problems, Basically, it finds and uploads only the data that's needed to run the particular simulation you do, which gives you a lot more speed, okay? It solves the I/O bottleneck on the cloud servers, which is a big issue for most types of synthesis and simulation problems, leveraging NVMe. And it also makes you multi-cloud compatible. So you're not married to the particular cloud that any vendor chooses. It's the same scripts, the same tools, the same solution across the board.
Does Holodeck compete against a Synopsys or Cadence or Mentor?
I don't think so. I think it's complementary. It solves the data movement problem, which they're not particularly.
What's a speed up?
on.
What are you talking? Relative speed ups?
Anywhere from 5 to 25x.
Okay.
So it's significant.
Okay.
Yeah, I mean, we've published, AMD has been using the tool for quite a while. There's a bunch of publications and videos where they talk about it. And we're showing it in the booth running, accelerating Synopsys, accelerating ANSYS, and accelerating Cadence, Virtuoso, and even Calibre. So you can get a big boost in speed when going to the cloud.
Okay.
Save money on licenses. And you can even do it with your own private data center. Do you need some help there?
Yeah, my brain is jamming because she's trying to send me a message. I have no idea what the message is. What is the message? Okay, something IP management. IP management.
Yeah. I think your question, IP management. What's happening to IP management?
I had a question here about IP management, but isn't that the same thing with Holodeck? And
No, Holodeck is about cloud bursting. IP management is about taking that gold mine of IP design that's in your company and actually leveraging it, right? The problem is that designs are getting more complex. Okay, the data is spread out over the globe in multiple data centers and multiple repositories. Companies are buying other companies, merging, and they end up with 7 different data management systems. And the people in one part of the organization don't know about the designs that were done in another part, and they can't leverage them effectively. Okay, so we've created IC Manage IP Central, which creates a holistic view into every DM system known to man. Obviously, it connects into the IC Managed databases, but it also connects into ClearCase, Perforce, Design Sync, Git, GitHub, GitLab, GitFun.
So it's a giant library of all your company's designs. So if I see
correct, and it automatically creates a catalog,
okay.
Gives you a Google search on top of it, can handle 100 million IP objects, and gives you full traceability and a time machine kind of view into it, so that you can pull that data in, and basically make it happen. It's not PLM. It's not putting together a little bomb. It integrates with the PLMs, but the key is now you can take advantage of the gold mine of data that your organization has.
I was going to just ask Tony that. What's the difference between this and PLM? It sounds a lot like a product lifecycle management bill of materials type thing. We're just putting it all together.
We don't do little bombs. We do big bombs in Team Center. So we introduced something called semiconductor lifecycle management with Team Center. So what we looked at was Team Center is the most proven, scalable PDM tool in the world for the discrete manufacturing side. And we looked at that and said, can't we apply this to what we see in semiconductor lifecycle? And what we're seeing is companies are coming to us and say, look, new product introduction is a problem. How do I manage my supply chain? How do I collaborate with them? Program schedule, timing, how do I keep that going? How do I manage the configuration of all the data I've got? What do I do with the bill of material? And so this is growing rapidly for us. And we've got major accounts, that are coming on board. Global Foundries started using it. We got Micron using it. We've got Samsung using it. Samsung came to us because Samsung uses us holistically across almost everything they do with our products, right? And so they came to us and said, we've got Teamcenter today. How do we use it for all the things we're talking about? So it's not the little bomb that we're worried about. We're scaling this to be able to handle the supply chain, the program, everything you do. So Teamcenter is well beyond just, it's not managing files, it's managing configuration as well. Back to the binning process I spoke about before.
Dean?
And it's all great. It's PLM, it's product lifecycle management. It's not a database for your engineers to find the pieces and parts that are the right pieces and parts for them to incorporate into a semiconductor design. The PLM system, still teaches the chip as one thing, okay? Because there's one supplier that makes it.
All right, you were saying the parts. You're saying your stuff is for the parts of the chip.
Parts of the chip. It's for the IP. It's IP that I'm talking about here, and it'll have a different instantiation, and it'll probably be revved for that particular use, or it might not be. Okay, and we all know that assembling the chip, okay, and the IP configuration that comes into that is done by the design management system. It's not done by the PLM system. It's a different problem you're trying to solve. It integrates, and the PLM is really important, and it's awesome, okay, but it's slightly different.
And I would agree with that. I mean, you can decide what level you want to manage that, and we'll continue to develop there, but a partnership between what you do and we do makes a lot of sense.
Let's do it!
All right, I want to go to some EDA stuff. This is just straight old EDA stuff, which I know.
Please.
Prakash.
Okay.
You just announced, which I gave a number 2 on my cheesy musty list, Sentries, Real Intent Sentry. And it was a security sign-off tool because it looked at all the different holes going on inside a chip design. The big thing you were talking about was you're static and your competition is formal. Why should I care?
So, well, first of all, thanks for giving me time to catch my breath after all that twin talk and the energy. I mean, it was like, took me a few minutes. Okay, so thanks for that. So before I go in there, Sentry is about hardware security sign-off, and as we are a static sign-off company which is enabling left shift for all your different verification processes. Similarly, Sentry has been designed to enable shift left for your security sign-off to make sure that data transfer integrity is free of any interference or leakage. And the way the product works is that the security architects and designers specify the rules, and then at RT level, the product analyzes and points out potential failures. Now we come to the static sign-off. So the competition that you mentioned, John, is...
which would be Jasper, VC Formal, OneSpin.
Formal tools. Basically formal tools, and formal tools are great because they can precisely either prove a problem or precisely give you a counterexample for the problem. The only challenge is that the capacity is limited to 2 or 3 million gates max. Now here with Sentry, with static approaches, we can process 5 million gate design in a couple of minutes, 100 million gate designs in a couple of hours. Now, the catch is that static sign-off necessarily produces noise, it produces false failures. But you can sign off on those false failures and then you have a sign-off. And if you run at 100 million gate, you run the formal tools, the tool will not finish in a year. So how do you solve a problem that you are simply not being able to solve today, early, and with some degree of reliability? So that is the differentiating factor that's behind Sentry.
Yeah, I did some math on it. It was a 12x speed up difference between using a static approach and a formal approach for 100 million gates. And I was like, okay, that's why that made number 1 for me.
So to that math, John and Cash.
Did you see my math on that?
I saw your math, yeah.
I mean, 100 million gates.
So I wouldn't say it's not true, but I think there's a nuance I'd just like to...
I estimate it would take about a year for Cadence to do it.
And it's the point that, I think that this kind of static security, I mean, it's a great idea.
He does it in 5
right?
hours, and then his guys have to do 3 extra weeks.
And of course, if you find something, right, that's a real thing that the design team need to go take a look at. But if it checks clean, it doesn't guarantee that your private keys are private.
Say that again. What do you mean?
Trust.
It checks clean.
So
Explain that.
if you pass all the warnings, so if you pass the static checks, because there are certain things that you can only do with formal, you're going to have to model check to prove that is absolutely secure. So I see them more as complementary. It's not like you can only do static and then not do the formal. But likewise, if you only do the formal, your point is valid. It's going to be way too high effort to find a bunch of things.
Yeah, hair doctor
so I think
formal has to do it.
My view is you still need both. And so I think I support what Real Intent are doing, but I think that kind of formal model checking, security path verification is still needed for sign-off.
So Paul, I'm sorry, but I will have to disagree with you that you don't necessarily only need model checking is the only way to sign off that a secure key cannot be accessed incorrectly or improperly. What we have done is that's exactly what we do. The reason why static sign-off works is because the onus on static sign-off approaches is that they cannot miss a problem. That's the only way you can achieve sign-off. So even though they are noisy, but if they can say that you do not miss a problem, then once you have dealt with noise, you have sign-off. And how we do that is a secret sauce. We have our own, we spend years developing customized technology to be able to analyze problems and to be able to provide that assurance. So yes, if your assumption was correct, your statement would have been correct, but no, we do stand behind that. We will guarantee if you use the product correctly that the secure keys will not be accessed improperly.
Okay. Shankar, IC Compiler and IC Compiler 2 were disasters. Absolute disasters. It allowed Anirudh to get Innovis, Genus, Tempest into the market and basically kicked Synopsys in the bad spot. And how did you clean that up?
So I always go to my customers for inspiration. So if you look
Did you clean that up or did Sassine clean that up?
We are inseparable, joined at the hip. We swim together, sink together. That's how we are in our journey together.
No, but seriously, how did you clean that mess up? I mean, it was a multi-year fiasco.
So basically, if you look at advanced node implementation, right, with sign-off getting so complex as it's getting at 2 nanometers and below,
right?
You basically, if your place and route is not correlated with your sign-off, it's tons and tons of iterations, lots of margin added to place and route. If your synthesis does not correlate with your place and route, tons and tons of iterations, more margins added to synthesis. So essentially, the landscape was do synthesis, even though with design compiler with lots of margin, do place and route with lots of margin, and then hope that you can converge in ECO with prime time. But to solve this problem, we went back to the drawing board and we completely rewrote our entire implementation franchise. We built a common data model.
Yeah, because you had 3 database models beforehand.
Right. So we built a common data model, right?
Yeah.
Had prime time timing running through front to back, place and route synthesis, all the way to sign off. So no miscorrelation. Correlation is addressed by construction. Common engines, because it's one data model, so same placer in synthesis, same global router in synthesis, same in place and route, so there's no mismatch between your synthesis placer going left and your place and route placer going right. And all that essentially delivered a convergent implementation in a single cockpit. So essentially, an RTL designer could start at the beginning and tape out DRC clean GDS at the end, all in the same environment. This was basically Fusion Compiler. Today, all of the top 20 customers use Fusion Compiler. Companies like Intel, Samsung, Qualcomm, NVIDIA, AMD, Microsoft, Google, you name it. Pretty much all the big companies. And also, what is really interesting is for companies that you may not list in the top 20, recently I was informed by my team about an AMS customer that dusted off an old implementation flow, fired up Fusion Compiler, 20% power savings. That's what you have left on the table because of all the margins in synthesis, all the margins in place and route. And 20% power is essentially a half node improvement. Now, on top of that, we essentially wrap DSO.ai to basically automate and make autonomous the entire parameter exploration that is so central to the implementation process. And that basically unlocked a big productivity gain. And so now pretty much all our top customers are using DSO to implement their designs. So Joe, AI does work and it does give some incredible results. And on top of it, basically this combination of a unified cockpit, unified data model for synthesis, place, and route timing with AI wrapped. It's been 5 years now. We still don't have competition in anybody else who has achieved this. I am going to repeat, there is not a single other vendor who has a unified data model, synthesis, place, and route sign-off system in the market today.
Paul?
I think we feel pretty good about the level of integration across our flow. And look, I think in the end, it's that front to back, you say, the performance, the results, the other things. I mean, I'm completely aligned with Shankar. That integration of the engines front to back is the right strategy. Cadence has been on that path, I think, for the same period of time. I also concur with the parameter space optimization, using AI to do this kind of gradient-free exploration of all the different knobs and settings. It really works. It is absolutely mass deploying. About the nuances of Shankar's statement, but I think we feel pretty good on the integration front.
What about the unified database model? Synopsys being the only one?
Yeah, no, I think...
Does Cadence have a unified database model?
I believe so. Now,
I believe so.
I would say, well, the nuance that you've got with that a little is, see, as you change the level of abstraction through the flow, like if you haven't tech mapped to gates and it's still a generic model, what does it mean to say have exactly the same form of analysis? But the moment that we are mapping into gates and we're in the placement world, we are fully unified.
Oh, GDS
Yeah.
I want to contrast the term integrated from the term fused. They're not the same thing. Integrated, you can take 3 different tools with 3 different data models and make them handshake reasonably well.
Yeah,
Passing
like IC Compiler and IC Compiler
APIs,
2.
whatever, right?
Right.
Fused is one data model, all engines implemented on the same data model, and then you truly get that next level of fusion, which is why you get the PPA and all the benefits of Fusion Compiler.
Let me ask the John Cooley question.
Yep.
So what? Who cares?
Yeah,
Right?
results matter.
So
Results matter. So what
Results
matters
matter.
when a customer...
And so whoever gives the better results, that's all
Right.
that matters. Whether it's integrated or fused or taped together or duct taped or glued or banana, it just doesn't matter. Like as long as the results are
The way
there.
to get good results is by getting the architecture right. If you don't get the architecture right, you'll always leave something on the table.
I don't know if I think that's one of the ingredients, but in the end, I mean, there's a lot of NP complete problems through the flow, right? How do you do the numerical placement? How do you do the clock tree synthesis, the routing? So I think actually those core engines through the flow, we need to keep a focus on those too. And there's always room. I still believe there's another 20% to be had from improving the placer. There's another 20% to be had from improving logic optimization. There's still a lot of juice.
You're saying because the margin in each stage.
The problems are just really hard. They're NP complete.
Well,
They're not
no
tractable.
Margins in the synopsis flow, by the way.
It's not just
No,
the
there is no margins
it's the
because you've
optimization.
got sign-off timing running front to back. Why do you need margins?
I think there's some margins in sign-off timing. Last time I checked.
Sure, sign-off to silicon, of course. But no, you don't need to put margins
Maybe
in
better
your
say
flow.
there are going to be distributions because your accuracy goes up through the flow. So you need to center the distributions, but there is still a distribution. Delays will change, right?
Architecture matters.
So John, if I may just
go ahead.
I work in a totally different domain, but I will disagree that integration is. I mean, while integration is extremely important from the point of view of efficiency, from the engineering efficiency, product delivery, everything, I don't believe that integration is the best way to produce the best solutions. I mean, what we have done is we have multiple applications. Of course, they're built on the same integrated platform. But in the end, we end up optimizing for each application, and we find that there are conflicting requirements. So we can't put them in the same binary. So we have actually specific, even though derived from the same engineering platform, we actually have specific products that are optimized, and that's why they do, competitively, they benchmark very well. So yeah, if there are margins and you have one platform and then you can do everything in there. I mean, my experience in my RTL world is slightly different.
Okay.
You know, I never said unified data model is easy. It's incredibly hard. Companies have sunk trying to do unified data model, or nearly sunk trying to do unified data model.
Every data
Present
bit
company
is
accepted.
huge. Yeah. It's like,
Yeah, but you know, the thing is, because it's hard doesn't mean you shouldn't try it. Because when you do succeed, the results are sweet.
Okay. Tony, it's been 7 years since Siemens acquired Mentor. Wow. Was that a disaster?
Hey, we got Wally.
I thought this panel was supposed to be over by now. No. In fact, in 7 years, we've doubled the revenue from where we were. It's gone extremely well. I would say...
Meaning like Mentor, if it was running by itself, it'd be double the
Exactly.
revenue. Okay.
Right. And Wally's here in the audience. Wally did a nice job of setting up a lot of great pieces. And outside of the IC space as well, it's gone extremely well. So for example, in the printed circuit board space with Expedition, we do very, very well. We've grown that business considerably because of the integration of what we bring.
Numbers.
Unfortunately, at Siemens, I'm not allowed to give numbers, as you know, outside of the division level.
Wally, are you here? Can you give us numbers?
All these numbers might be a little dated at this point, but
you can say overall, it's
the other part I would say is earlier I was on the panel with Jay and we had Dassault Systems up with us, and there's accounts like Airbus where we do a little bit computational fluid dynamics. We do very well. You mentioned ANSYS. If we're not the leader, we're neck and neck with ANSYS on fluid dynamic calculations and things. So we're all over them with that, but they don't use a lot of other software from us because they use Dassault Systems, being a French company. But we've gone there and also into Boeing commercial. Boeing Defense uses us across the board, but Boeing commercial, same thing, use a lot of Dassault. And in both those cases, it's what Wally and the team put together with the electrical systems capabilities we have for wire harness, electrical system. We do extremely well there. And it's allowed us to go into those accounts.
You're saying you displaced Dassault, is what you're saying.
For those areas, they didn't have an answer. So believe me, if they had an answer, they would have came in and used Dassault. And we've been able to come in and show that. So across the board, it's been really good in what we do with Expedition, what we do with electrical systems. And then in this entire EDA space, again, we've essentially doubled the business. So we have a lot more to do. And it's not been easy. And the reason, and I sat with Sassine at dinner a few weeks ago, we were talking about it, and he was asking for my advice as to how to integrate PLM and EDA together. And I laughed and I said, well, I'm not sure I really want you to be successful with that, but it's a different sales approach, a different sales cycle in a lot of ways. But I think we've done very well with it. And then finally, the best part about it is the multiple we paid at that time, 4. Think about where we are today.
Yeah, and if you doubled your revenue, so.
And think about what's happening. You got multiples of revenue multiples of 15, 17. You paid 4.
Good deal.
So, good deal.
Well, when the billionaire says it's a good deal, it's a good deal. There you go. So, thank you, Dean. Paul.
John.
He mentioned CFD. You have some sort of CFD stuff, and Shankar is paying $31 billion for CFD stuff. Aren't you in trouble?
No, I mean, I brought that up earlier. I think
Which is your Clarity tools, Clarity CFD, yeah. So.
Yeah, well, Fidelity CFD.
Fidelity.
So if we're talking about ANSYS mechanical,
right.
That mainstream space. So I think now combining, the pre and post processing with the meshing, with the core solvers, I think we've been very smart. We've done a lot more of these kind of tuck-in acquisitions, so nothing to the tune of ANSYS. But I think we feel very well positioned in this point that we have been able to combine it with some of the core expertise in our electrical space and Anirudh's deep knowledge on this highly scalable, accurate solvers. So I think we're very excited, but we acknowledge, of course, right, we're in that ramp phase, right? We're not at the scale of ANSYS right now, so let's see how it plays out.
Are you displacing customers from ANSYS?
We're getting a lot of good wins, yeah.
Who?
I'm not going to go into them.
All right, I'm going to ask a personal question. Tony, Joe Sawicki is gone. Does that mean Caliber is going to be dying and Shankar is going to be moving into your space?
Well, first of all, Joe's not gone. I mean, for some of you who don't know, Joe's had some health issues, and I won't get into.
But I mean, Mike Ello has taken over.
But yeah, we've had to make a change because he's dealt with that for some time. And
but Sawicki ran the Tiger team that ran Caliber, and he was the heart and soul of Caliber and going after it and making it happen. And
he did. But I mean, look,
that's like Stephen Jobs being bumped from Apple. It's like, you know.
But even Joe would tell you. I mean, we've had many discussions. Look, he was towards the end of his cycle as well, as far as being in this space and where he's going to go. So we started succession planning years ago. That's how we do this. And there's a lot of look. My organization has 25,000 people in it. There's constantly people that rise to the occasion of what needs to be done. And the great thing about what's happened with Caliber is that wasn't just Joe. There's a great number of people there that are driving this forward, and they're part of that succession planning, and they're part of the team that helped build that. And Joe would tell you that himself, right? That they drove it. So we feel really good there. We continue to do well, and a lot of the same talent there. And while everybody's trying to come after us on Caliber Testnet, we're going to come after people on place and route. So I mean, it's part of competition. We're going to go, and so we feel good about where we're at.
Shankar, are you going to lose to Apresia?
No, but firstly, much respect to Joe and the Caliber team. I mean, building a sustained long-term leadership position in this industry is hard, and much respect to that team. But I'm actually very bullish on physical verification because if you look at the rule complexity and you look at the number of rules at 3 nanometer, 2 nanometer, 16 nanometer angstroms, and so on, right? The throughput and the runtime of DRC is ballooning. I think we believe we have the best architecture to deal with that kind of explosion of complexity. Same-day run sets for all the advanced nodes across multiple foundries. And most importantly, really compelling customers like Intel, like NVIDIA, like Cisco, MediaTek, AMD, all using our physical verification platform. So I'm actually quite bullish that with this...
For sign-off.
Pardon me?
For sign-off.
For sign-off, yep.
Not Caliber. They're using ICV. Are you saying ICV?
They are, yeah. I mean, NVIDIA
ICV.
tapes out their entire top-level GPU with ICV.
And
Intel
TSMC says that's okay.
Absolutely.
Wow.
Absolutely.
Okay.
Please check with TSMC and you will get a resounding acceptance of an ICV taping.
Well, Cadence tried that with Pegasus.
My guys are all shaking their head the other way over there, but that's okay.
Well, Pegasus is... Yeah, I would like them to be...
Pegasus tried to say...
Let's put a benchmark in. Let's benchmark it. Let's do that, okay?
I have first down. I mean, take out the last Palladium chip with Pegasus. It's a massive chip, phenomenal scalability. It was excellent. Absolutely excellent.
You're saying your 5 nanometer Palladium chip was done through Pegasus?
Yep.
Not Caliber, not Synopsys, ICV.
No. And I think the same go to TSMC. I think we're bringing on the competition now, and I'm totally with Shankar. I mean, just that rule complexity and the size of the chips, you just have to have this phenomenal throughput, and that's something that, I think we've both been building things from the ground up.
So, and what Tony is saying is we have a huge staff and we thought it's all thought out.
No, it's benchmark us.
Yeah.
Let's go.
Yeah. Competition's good.
All right. So, Paul.
John.
Shankar is coming at you, coming at Virtuoso, particularly in analog migration. And he's gunning for you. Virtuoso is going to be in trouble if he gets a foothold in there. What are you going to do?
Well, so I think we're very privileged, right, to have just such a phenomenal custom and mixed signal franchise with Virtuoso and Virtuoso Studio.
No, Studio's new.
Exactly. So I was going to say,
Virtuoso is 30 years old, but Studio is new, and what Shankar has is new.
Exactly.
So
and I think this change,
but
we talk about migration. Remember, Tom Beckley's company, right, Neolinear. That's 20 years ago. That was automated circuit sizing, automated layout. I mean,
but
we've actually had a huge amount.
It did pieces of the puzzle.
And we've continued to march. And I think there's a huge opportunity with AI. So Virtuoso Studio bringing out AI-driven migration. We also still, there's a few more acquisitions, right? We've had MuniDA, we've had Pulsic coming in. So I think we feel, really bullish about the automated migration within the Virtuoso platform. And one point I'd point out, John, I think no matter what we do with automation in custom design, it's always going to be highly interactive, right? There's always going to be that human in the loop. And to some point, you've just, that environment, it's a little bit like Microsoft Office, right? We've got to put that automation, but within the actual Office Studio, in this case, the Virtuoso Studio. And I think that's something that is really, really hard to replicate.
But I've seen custom compiler Credo benchmarks, and wow, they work. I have not seen Virtuoso Studio benchmarks where they're wowing the competition.
I guess there's an action on us to share some more with you on that front. No, I think it absolutely is working. I mean, it's still relatively early in this market, but we're going to see over the next 3-5 years, I think, a phenomenal uptick in automation in custom design. And so, I think we feel really well toward both organic innovations and tuck-in acquisitions to continue to do that, but within that phenomenal interactive cockpit that is Virtuoso.
All right.
So, I think welcome the competition, but we're ready for it.
So I'll flip it around. Shankar, I know for a fact Virtuoso's in 20 of the top 20 big boy logos. I don't know of anybody using custom compiler.
Okay, so let me give you.
How do you surround the enemy when you have no soldiers?
Some surprising news maybe to you, John. All Intel custom data paths are designed with custom compiler. A large percent of internal Samsung IP development is done with custom compiler. Companies like Toshiba and Panasonic Nuvoton have completely switched over to custom compiler as their primary platform. And then the world's largest mixed signal IP group, which is the Synopsys Solutions Group, over 7,000 mixed signal engineers use custom compiler day in and day out to deliver the best interface IP and foundation IP.
Well, do they have a choice?
No, but hey, in the end, for anybody here that's looking for a modern...
In the Soviet Union, everybody is happy. Nobody leaves the Soviet Union. We have walls here, so nobody leaves.
That's looking for a modern analog design platform, high productivity, AI built into it to enable optimization and migration. Custom compiler is your choice. And with ASO.ai, we have solved what I believe has been one of the long-standing issues in analog design, which is all the previous attempts at migration and optimization were stuck because they were done for specific types of circuits. There was no general approach. What we have achieved with ASO.ai is we have cracked that problem with a general approach, regardless of circuit type, to essentially optimize analog circuits and migrate analog circuits across nodes and produce exceptional results. And that's why the traction on that technology is extremely high, and we're getting pretty much a wide number of opportunities to take a crack at the...
So,
hey, John,
go ahead, Joe.
Can I make just a general comment? So your brand and what you're about is the engineer, the IC design engineer on the ground making things happen. There's a lot, I'll take a lot of talk on this panel today. I mean, one of your jobs is to give their engineers an overview of what's going on, and you do a great job with, your cheesy list and what's going on in the show. Lots of the discussion here, but a lot of this doesn't really make a difference to the engineer, actual engineer. All of this talk about CAE is bullshit to most actual IC design engineers, and will be for most of their career. That stuff is different, and you have to realize that, these companies are making a choice. Before I left Cadence, by the way, we thought about buying a big CAE company. That was one of the thoughts that we had at that time. We decided against it. It's a different business, a different customer base, right? So that's a different business. It isn't going to affect your actual design engineers, except at that narrow place that's the intersection, like 3D IC design. That's number one. Number two, there's a lot of conversation here that's extremely important at the corporate level of the design automation organization for the company. I'm not saying that's not important. I built one of these companies, guys. I understand that world and selling into that world. However, you got to remember the actual engineer in front of their workstation. They're the guys that drive all this stuff. They're the ones that are doing the design work. And they got to have fun. It's got to be interesting. Yeah, they need some information, but kind of right now they're in lockdown, right? With all of these big...
Well, that's why I was saying the spec comes in, and I'm just working with, I'm designing against the spec.
And what tools they're supposed to use.
I'm actually more interested in what Shankar said. So you said Intel, Samsung, who else?
Toshiba, Panasonic, Novaton.
Panasonic, and then some large unknown company.
It's called the Synopsys Solutions Group.
Oh, that one. Okay. All right. So you're claiming 5 analog migration customers.
I'm giving you examples of large companies doing
I see
meaningful
4,
design.
but okay, and 1 North Korean prisoner.
It just happens to be the best IP team in the business.
North Korea is great.
Who cares, John? Who cares?
Because you want to know if it's real or not. That's the thing. It's if he had no logos, then he's in trouble and he's just blowing smoke. But the moment now he has 4 logos plus a half, so 4.5, it's a threat to Cadence, at least as possible in that one space.
I think there's still a lot of virtual studio use in those accounts.
Well, I'm only talking about studio type things.
Yeah.
So
Yeah, but what's the actual engineer getting? That's what I want to hear.
Okay,
What's the engineer
let's
getting
talk
better?
about that.
What's the engineer getting better from you versus him?
If we believe that analog migration and automatic analog optimization is a high-value problem, the engineer is getting a lot. They're saving days, weeks, whatever of effort,
I believe that.
which they're doing by hand. And now you have a way to do it automatically.
And you do that, they can't.
yeah.
That's my claim.
Yeah, that's a big deal.
Check me out.
Thank you.
All right, thank you.